Hello, welcome to today's session of organic chemistry. In today's session, we'll be talking about a very important and interesting molecule in organic chemistry, and that is benzene. So this is the electronic or the orbital structure of benzene molecule. So the molecular formula for benzene is C6H6. If you see the structures, these are resonating structures. Benzene, you can draw two resonating structures for benzene, and it's a cyclic structure, right? And there are 6 carbons, the corners of the ring, 1, 2, 3, 4, 5, 6, 6 carbons and 6 hydrogens. Each carbon is connected to a hydrogens. So the molecular formula is C6H6. It's a cyclic molecule. Looks like there are single bonds and double bonds in alternating position, right? So if that's one of the possible resonating structure, you can also draw a resonance structure for this, right? So you can basically move this double bond here, move this double bond here, move this double bond here, and you get this structure. These are resonating structure. And what it also tells you is the pi electrons, which are here, here, and here, the 3 pi bonds constitute 6 pi electrons, and these pi electrons are free to move. These are delocalized throughout the ring. They can move throughout these 6 carbon atoms. Okay, as a result, you can draw a resonance hybrid, and this is the structure of the resonance hybrid. The ring on the center represents the delocalization, the free movement of the electron, the pi electron, through the ring. Or you can draw it this way with this dashed ring. Okay, so benzene, C6H6, ring system, conjugated, meaning the electrons are free to move about, free to move through the ring. And it's also planar. Okay, if you see the structure here, though we draw it vertically like this, and not a lot can be inferred from this vertical structure, but if you look at from a side angle view, the molecule benzene is actually flat, and the black solid lines are the carbon-carbon sigma bonds. The p orbitals are the orbitals. The p orbitals are carbon that are participating in the pi bond formation. And yeah, it's a planar flat structure. Okay, so it's a cyclic planar. It's a conjugated system, right? All these carbon atoms are connected via the pi bond, and the pi electrons are sort of moving throughout the ring. Conjugated. Okay, so cyclic, planar, and conjugated. And if you have a cyclic, planar, and conjugated system with this number of pi electron, any of this 2, 6, 10, 14, 18, and the list goes on. In the case of benzene, we have 6 electrons, right? 6 pi electron. So if your molecule is cyclic, planar, and conjugated with this number of pi electrons, that system is called aromatic. Those molecules fall under a special category of organic molecules called aromatic molecules. And benzene is an aromatic molecule. That's why my title, the topic here says it's not an alkene. It looks like an alkene, right? It looks like a cyclic triene, but it's not an alkene. It's an aromatic molecule. Okay? It has aroma, of course, but the name is more than that. The name aromatic does not only suggest that it has a sweet smell, but there is something fundamental in its electronic property, in its chemical property, and because of which it falls under this category of aromatic system. Okay, so benzene is an aromatic molecule, not an alkene. That's the first thing I'm going to tell you. It's a fact. Now, let's try to justify the fact. How can we say benzene is different than alkene? How are the properties of benzene different than alkene? So what we're going to do here is we're going to talk about these 3 important factors that will justify that benzene is actually much, much different from alkene. Okay, it's a class of its own. It's a aromatic system. So the 3 components are, first we're going to look at bond length and see how the bond length of benzene would tell us that it's different from an alkene. Then we're going to look at the heat of hydrogenation. We're going to look at the amount of energy that's involved in hydrogenation of benzene and see how that number can be used to distinguish it from the other alkene. And we're going to look at the chemical reaction that benzene follows or benzene undergoes and how those chemical reactions are different from the reaction that alkene family undergoes. Okay, so bond length, heat of hydrogenation, and chemical reactions. Okay, let's talk about bond length. So what I've done is, there's a lot of information in this slide, but I want you to be a little bit patient with this. So a regular carbon-carbon single bond is 0.153 nanometers in case of cyclohexane, right? If it's a cyclohexane, this is an alkane, a cyclic alkane, the carbon-carbon bond length in this is 0.153. Now, a carbon-carbon double bond length is 0.134 nanometers in cyclohexene. So this is an example of cyclohexene, which is of course an alkene, a cyclic alkene. Here the carbon-carbon bond length is 0.134 nanometers. But when the experimental studies were done, when the X-ray structure of benzene was studied, what was found was that the carbon-carbon bond length in alkene is 0.139 nanometers, and all the bonds were identical. That's pretty surprising, right? If benzene were an alkene like this, the one shown here, then 3 of the bonds should have been 0.134 nanometers, the 3 double bonds, and the 3 single bonds should have been 0.153 nanometers, right? But that's not the case. Surprising, that's not the case. All the bonds, the carbon-carbon bonds in benzene are identical, and they are 0.139 meters in length. So that suggests us that the carbon-carbon bond is somewhere between a single and a double bond. So what's happening is, these electrons are, since they are free to move through the ring, they move. That's why the bond actually is not fixed. The double bonds are not fixed. The double bonds conjugate, right? They resonate through the ring. As a result, all the bonds are like 1.5 bond. This is the actual resonance hybrid. So each of these carbon-carbon bond are not a single bond, not a double bond. They are 1.5 bond. That in between single and double bond length. And all of these bonds are identical. And the bond length is 0.139 nanometer. So that tells us from a bond length perspective that benzene is not an alkene. If it was alkene, let's name this molecule as if it were alkene, then that would have been 1, 2, 3, 3, 4, 5, 1, 3, 5, cyclohexatriene, right? It's a cyclohexene system, but there are 3 double bonds, so it's a cyclohexatriene, and the double bonds are present in 1, 3, and 5 position. If it were an alkene, the name would have been 1, 3, 5 cyclohexatriene, but this is not an alkene. This is a totally different class of organic compound. It falls under the aromatic compounds, and this is the actual structure with all the carbon-carbon bond lengths being identical. Okay, I think this picture is missing a little bit here, but if benzene was an alkene and there were single bonds and double bonds in an alternating position, then the shape would look something like this. Pretty weird shape, right? A long single bond, a short double bond, a short double bond, long double bond, something like that. But no, the actual structure of benzene, proven experimentally, is a perfect hexagonal, which means all the bonds are identical. So the bond length and also the shape of the molecule tells us that all the carbon-carbon bonds are identical, and it's not an alkene. It's not 1,3,5 cyclohexatriene. It's not. Okay, that's the first factor that tells us that benzene is not an alkene. Now the second one, we'll look at the heat of hydrogenation. Okay, so let's start here. Look at this molecule first. This is cyclohexene. It's an alkene family. It's a cyclic alkene family. So if you hydrogenate this guy, the heat of hydrogenation, the enthalpy change in hydrogenation is negative 120 kilojoules per mole. Okay, then what? Now let's look at this guy. This is also alkene because it's not a completely conjugated system. The pi electrons are not delocalized throughout the ring. So this is still alkene, a diene, a cyclic diene. If you hydrogenate this guy, the heat of hydrogenation involved, the enthalpy change in hydrogenation is negative 232, which is almost a double, right? Now, let's go to the benzene molecule. Now, if this guy were an alkene, right, then the heat of hydrogenation for this guy should have been thrice almost thrice this guy. So around negative 360, right? This is the predicted if it were an alkene. But what was found was through the experiment, the enthalpy change was only negative 208. Why is the enthalpy change so less? What makes this molecule that much stable, right? And that stabilization is because of the resonance, because of the cyclic conjugation that existed in the system, and that made this molecule not an alkene but an aromatic molecule. That's the aromatic stabilization, you can call it, or we call it resonance stabilization. The difference between negative 360 and negative 208 is 150 kilojoules per mole. That's the amount of energy, the stabilization energy that benzene has because of the aromaticity, okay, or because of the cyclic conjugation of the pi electrons. So the heat of hydrogenation is also indicating to us that benzene is not a triene, it's not a cyclic alkene, but a molecule in itself, a different category of molecule, okay, which is basically aromatic molecule. And that this phenomenon, which tells us that it's much more stable than a triene by a factor of 152 kilojoules per mole, that stabilization energy is called aromatic stabilization energy or resonance stabilization energy. Okay, the difference between the theoretical or expected versus the actual. Now let's go to the third factor. Before going into the third factor, I want you to see this pretty cool orbital structure of benzene. This is basically a molecular model which you can construct using the ball and sticks. This is a two-dimensional structural formula of benzene, not the actual formula, because not the actual structure, because in the actual structure you don't have this distinct double bond and single bond. All these bonds are 1.5 bonds, all identical bonds, right? And this is the orbital structure. See, these vertical p orbitals, those are the p orbitals of carbon that are participating in formation of pi bonds. The orange lobe between the carbon-carbon, that's the sigma bond. And the orange lobe between the carbon and hydrogen, that's the sigma bond between carbon and hydrogen. So the orange sort of lobe represents the sigma bond, and the vertical p orbitals are responsible for making the pi bond. The lateral overlapping makes the pi bond, the head-on overlapping makes the sigma bond. So there are basically 3 pi bonds, and let's see how many sigma bonds are there. 1, 2, 3, 4, 5, 6 sigma bonds between carbon and carbon, and also there are 1, 2, 3, 4, 5, 6 sigma bonds between carbon and hydrogen. So there are 12 sigma bonds and 3 pi bonds, if you were to break down the number of pi bonds and sigma bonds in that way. Okay, so that's the side-on orbital structure. This is the top-down orbital structure. So there's a red and blue stuff. These are the p orbitals of the carbon that are participating in the formation of pi bond. The black line is the sigma bond between carbon and carbon, right? You are looking at the molecule from the top, the flat molecule. It's a planar molecule. And this is also a fused orbital structure, a side-on diagram for the fused orbital structure of benzene. Okay, so we looked at aromatic stabilization through the heat of hydrogenation. We did look at the bond length and the molecular structure, which indicated and which have justified so far that benzene is different than the alkene. It's not a triene. It's a different category called aromatic molecule. So the third one, let's look at the chemical properties. Let's look at the chemical reaction that benzene undergoes and how they are different if they are from alkene. We would expect them to be different than alkene, right? This is a linear alkene, 1,3,5 hexatriene. This is a cyclic alkene, cyclohexene, and this is benzene. Now, catalytic hydrogenation is possible, but at much higher temperature and pressure. Remember, we did catalytic hydrogenation of alkene. Well, you need a little bit of higher temperature on that, around 150 to 200 degrees Celsius, but the amount of pressure required is not as much. I think around 15 to 20 psi of pressure is enough to undergo hydrogenation, the catalytic hydrogenation in alkenes and cycloalkenes. But in case of benzene, if you have to hydrogenate this benzene, you need a lot more pressure. The pressure required is around 150 to 200 psi in the presence of a catalyst. That tells us that benzene molecule is pretty resistive towards hydrogenation. It's not wanting to do hydrogenation at room temperature. You have to enforce extreme condition for benzene to undergo hydrogenation, right? Tells us a little bit about this extra stability of benzene because of the conjugated system, right? The aromatic stability. So that's the first thing. The hydrogenation is possible, but only at extremely high temperature and pressure. The second one, we did electrophilic addition of halo acid, halogen, and water in alkenes. You can add bromine molecule, you can add HCl molecule, you can add water molecule to this triene. You can also do the same thing here, but in benzene that's not possible. Benzene is not going to do electrophilic addition reaction. Okay? Instead, it's going to undergo electrophilic substitution reaction. Okay? Which is different. Here you are adding, here you are substituting an electrophile. You're bringing an electrophile, attacking the system with electrophile and taking it out in electrophile. That's electrophilic substitution reaction. Here, the alkenes and cycloalkenes, they undergo electrophilic addition. This undergoes electrophilic substitution. Now let's see why, and let's look at the mechanism of one of the electrophilic substitution reaction is in benzene. So first thing, why does benzene undergo electrophilic substitution? Why is it of interest for an electrophile, right? If electrophile is attacking the system, that means this system should be reaching an electron. And it's pretty clear, right? There are these pi electrons which are mobile, so benzene is electron rich. So any electrophile, for example, here you have NO2 plus, positively charged, so it's an electrophile. This would be intuitively attracted to this benzene system, right? So benzene is reaching an electron, attractive to electrophiles first. Now, why does it undergo substitution and not addition? Why does it not undergo addition like the alkenes and cycloalkenes do? We'll see that. Okay, so what's happening here first? Let's look at the main reaction and we'll look at the mechanism and see why substitution is preferred. So NO2 plus is basically being added here. And if you are adding an NO2 here, that means the H atom which was originally attached here, it's gone in the form of H plus. So electrophile is attacking here and one electrophile is leaving, H plus, because you can't have NO2 and H together, right? You can't have NO2 and you can't have that H because carbon can't make 5 bonds. 1, 2, 3, 4. There are already 4. So that H was ejected out in the form of H plus. Okay, so this is called nitration of benzene. When you are using adding NO2 plus group into the benzene ring and removing H plus, that's called nitration. You can do similar other electrophilic substitution reaction in benzene, but we are just going to take an example of nitration. Okay. Now let's look at the mechanism. So this is the main reaction, the one that we just discussed before. So the mechanism is, in order to generate this electrophile NO2 plus, you use strong acids like sulfuric acid and nitric acid. So when sulfuric acid and nitric acid react, you generate this nitronium ion, NO2 plus, this one right here, and that's the electrophile. Okay, so if you look at the mechanism, you have sulfuric acid. This is the leaf structure of sulfuric acid. This is the leaf structure of nitric acid. Between sulfuric acid and nitric acid, sulfuric acid is more strong, so this would donate a proton. So the H plus from here would be attracted to the lone pair electrons in oxygen. As a result, the nitric acid would be protonated. So this is the nitric acid with the H coming from here, and the other half, the SO4 minus, would be a nucleophile, which is not shown here, but there is also HSO4 minus. Okay, so I'll write that down just for you to be clear. Looks like I can't draw, right? Oh, looks like I'm not being able to draw. Okay, let's see. Okay, looks like I'm being able to draw. So HO4 minus, that's also on the side. Okay, so you have H2SO4, HNO3. The H2SO4 will be the acid, because the strongest acid will donate the proton, so this will behave like a base. So the nitric acid is now protonated. So from this protonated nitric acid, the water will be a leaving group. So the water comes off. There is the water, pretty stable. So that comes off. Now you have this NO2 plus remaining. That's the electrophile source, electrophilic source. But you also need to remember that there's also the HSO4 minus ion. That's the remaining part of this sulfuric acid. Okay. So NO2 plus now is the electrophile. This is gonna go and attack this pi electrons, or you can say the pi electrons attack the N plus, the positive part of this electrophile, because this is reaching electron, pi electrons. So as a result, you get this NO2 attached to the carbon, and once the pi electrons are used, one of the carbon would be positively charged, and that carbon through resonance can move throughout the ring. So you can move this double bond here, and you can create a positive charge here, and you can move this double bond here and create a positive charge here. What this means is that positive charge actually is being stabilized because of the delocalization throughout the ring. And the important part is now at this point, this carbon has both NO2 and there is also H. This H part has not gone away, right? There was H here to begin with. So there's also H here. So let me write it down. There's also H here at this point. Now, what happens is that H, this is here, is going to leave his electron here, back here into the system. And either the water, either there is water here, or you can even use this HSO4 minus, because both of these are nucleophile, right? Water has electrons. It can attack a proton, H plus. This is also a negative charge. It can attack a proton. So the water is going to go grab the H plus, and the electrons are coming back here, and the aromaticity is stored, restored, right? So this is a really important step. The reason there is no addition here, the reason the H2O does not come and attack here and form an addition product is because if you do a elimination product or a substitution product, you can restore the aromaticity. That's a very important step. That's the driving force. In order to restore the aromaticity, the substitution reaction happens and not addition. Okay, so the H2O is not going to go and attack the positive center and make a OH here. Instead, it's going to go and grab the H plus, and the H is going to leave its electron here, and the aromaticity is stored. This part is very, very important. Restoring the aromaticity, it's written here. Okay, so H2O becomes H3O plus, you get a nitrobenzene. So basically, this last step tells you why benzene undergoes electrophilic substitution reaction and not electrophilic addition reaction, right? Basically to restore the aromaticity. So to recap, so what we talked about today is we looked at the structure of benzene and how the bonds are arranged, the connectivity, the carbon-carbon sigma bonds, the carbon-hydrogen sigma bonds, the pi bond formation through the p electron in the p orbitals in the carbon atoms. We looked at the general structure. We saw how benzene was a flat two-dimensional structure. And we also stated a fact to start with, right? We told benzene is not an alkene, it's an aromatic molecule. And in order to justify why benzene was different from alkene, we touched on this three important factor. We found out that the bond length in benzene, the carbon-carbon bond length in benzene was identical, and it was not alternation of single bond and double bond. So it's very different from the alkene. In terms of heat of hydrogenation, we found out that there's that extra stability in the benzene system, the aromatic stabilization or the resonance stabilization, that told us that it's not an alkene or a triene. And also we looked at few chemical reactions, right? We saw why benzene didn't undergo hydrogenation, the catalytic hydrogenation so easily. We also saw benzene didn't undergo electrophilic addition reaction. Instead, it undergoes electrophilic substitution reaction. And the main reason that benzene undergoes electrophilic substitution reaction was to restore that aromaticity during that last step of the mechanism, okay? So just keep in mind, just research a little bit more about benzene. It's a very interesting molecule, very synthetically useful in industry. It's sort of like a precursor for a lot of different useful products, petroleum products and other pharmaceutical products. So yeah, why don't you do a little bit of research on benzene and look at some of the chemical reaction that benzene undergoes. Yeah, so thank you for your time. I'll talk to you soon. Bye.